Look at the night sky. Every star you see, every faint dot, every galaxy glowing in silence, they are not where you think they are. Some of that light left its star before humans learned to write. Some of it began its journey before Earth even existed. So here's the impossible question. How do we measure something so far away that even light struggles to reach us? No ruler can reach the stars. No spacecraft can travel that far. And yet we know their distances. Not by guessing, not by faith, but by logic. Starting from what we can touch, science never begins with the impossible. It begins with what we can touch, measure, and verify. Before we tried to measure the stars, we first had to understand our own neighborhood. The closest large object to Earth is the moon. Its distance is about 384,000 kilometers. Today we know this with incredible precision, not by guessing, but by experiment. Astronauts placed mirrors on the moon, and we fire laser pulses at them. The light goes there, bounces back, and returns to Earth. By measuring the travel time, we calculate the distance. Simple idea. Powerful result. The Earth-Sun distance is about 150 million kilometers. This distance is so fundamental that astronomers gave it a special name, 1 astronomical unit. For over 2,000 years, humans had no idea what that number was. In ancient Greece, a thinker named Aristarchus tried to solve the problem using nothing but geometry and careful observation. He studied shadows, eclipses, and the angle between the sun and the moon when the moon appeared half-lit. His logic was sound. His math was correct. But his tools were limited. Without precise instruments, even the right idea can produce the wrong number. Still, Aristarchus did something extraordinary. He showed that the universe could be measured not by myth, not by belief, but by reason. That idea survived. Centuries later, with better instruments and better timing, humanity finally pinned down the Earth-Sun distance. And once we had that single solid measurement, the door to the universe opened. Because when you know one real distance for sure, you can use it as a ruler to measure everything else. And that's how the journey to the stars truly begins. The speed of light enters the story. At some point, rulers stop working. You can't stretch a tape measure from Earth to Mars. You can't place markers between planets. So science does something clever. It replaces distance with time. Today, we measure distances inside the solar system using radar. We send a radio signal toward a planet. The signal travels through space. It strikes the surface, and it bounces back. We measure how long the round trip takes. Now comes the key idea. Radio waves are a form of light. And light always moves at the same speed, about 300,000 kilometers per second. That speed is not a suggestion. It's a rule. So if we know the speed and we measure the time, distance becomes simple arithmetic. Distance equals speed multiplied by time. Elegant, reliable, almost magical. Using this method, we can measure the distance to the moon within centimeters and the distances to planets with astonishing accuracy. But then, reality hits us. Radar works only for nearby objects. Even light has limits. A signal sent to the nearest star would take years just to arrive by, years more to return. No human experiment can wait that long. So the speed of light, which helped us measure the solar system, suddenly becomes a wall. It tells us something deep. The universe is not built for shortcuts. Information does not travel instantly. Cause does not outrun effect. The speed of light is not just how fast light moves. It is the maximum speed of the universe itself. And once we understand that, we realize something profound. To measure the stars, we must stop sending signals and start using geometry, patience, and the motion of Earth itself. That's when the next chapter begins. Parallax, seeing depth in space. Hold up your thumb. Close one eye. Then switch to the other. Your thumb jumps sideways. Nothing moved, you did. That tiny shift is called parallax. It happens because your eyes view the world from two different positions. Your brain turns that shift into depth. Now imagine doing the same thing, but on a cosmic scale. Instead of your eyes, use Earth. As Earth orbits the Sun, we observe a nearby star in January. Then again, 6 months later, when Earth is on the opposite side of its orbit, the star appears to shift slightly against the background of much more distant stars. That shift is incredibly small, often less than the width of a human hair seen from kilometers away. But it's enough. Because we already know the size of Earth's orbit, simple geometry gives us the distance. From this idea, astronomers created a new unit, the parsec. A star 1 parsec away shows a parallax shift of 1 arcsecond. In familiar terms, 1 parsec equals 326 light years. This method was revolutionary. For the first time, humanity measured stellar distances directly, no guesswork, no assumptions. But the universe doesn't give up its secrets easily. As stars get farther away, their parallax shrinks. Beyond a few thousand light years, the shift becomes too small to detect, even with powerful telescopes. Space is simply too vast. So once again, science reaches a limit. And when that happens, it does what it always does. It climbs another rung on the cosmic distance ladder, standard candles measuring by light itself. Eventually, parallax fails. Stars become so distant that their tiny sideways shift vanishes into nothing. The universe stops giving us depth. So astronomers ask a different question. Not where is it, but how bright should it be? Some stars are special. They shine with a known intrinsic brightness. No matter where you put them, they burn with the same true power. Astronomers call these stars standard candles. Here is the trick. If you know how bright something really is, and you measure how dim it appears from Earth, then distance is no longer a mystery, it's arithmetic. Light obeys a ruthless rule called the inverse square law. Double the distance, the light spreads over 4 times the area. 10 times farther, 100 times dimmer. Nothing negotiates with this law. Not stars, not galaxies. Not whole. So by comparing true brightness to observed brightness, we can measure distances far beyond parallax. Entire galaxies reveal their scale this way. But the universe escalates again. At extreme distances, individual stars vanish completely. Even standard candles go dark. Then something violent comes to the rescue. Supernovae. When certain stars explode, they do so with nearly identical peak brightness, bright enough to outshine entire galaxies. These cosmic explosions become beacons visible across billions of light years. They let us map the universe on its largest scales. But notice the pattern. We are not traveling outward. We are not touching the stars. We are measuring reality indirectly using light itself as a ruler. The universe never lets us step outside our limits. It only lets us understand them. And understanding turns out to be enough. Supernovae cosmic flashlights. Eventually, even stars disappear. At great distances, individual suns fade into nothing. Galaxies become faint smudges. Light itself seems to lose the fight. So the universe gives us something extreme. Supernovae. When a massive star dies, it does not go quietly. It detonates. For a few weeks or even days, it releases more energy than its entire lifetime combined. For that brief moment, a single star can outshine an entire galaxy. That makes supernovae visible across billions of light years. They are not just explosions. They are cosmic flashlights. Some supernovae, called type Ia, are especially important. They explode in almost exactly the same way every time. Same physics, same mass, same peak brightness. That means astronomers already know how bright they truly are. So when we see one far away and it looks faint, we know it isn't weak. It's distant. By comparing how bright a supernova should be to how bright it appears from Earth, we can measure the largest distances ever known. This is how we mapped galaxies across the observable universe. But something shocking appeared. Distant supernovae were dimmer than expected. Not just far too far. The universe wasn't slowing down. It was expanding faster and faster. Space itself was stretching. This single discovery changed everything. It told us the universe had a beginning and a strange, accelerating future, all from dying stars. We never traveled there. We never touched them. We read the universe the only way it allows, through light. And once again, the cosmos reminds us it hides its secrets in explosions and waits for minds curious enough to notice. So what does all of this really mean? Every distance you hear in astronomy is not a guess. It is not a belief. It is not science fiction. It is a chain of reasoning, a ladder built step by step from what we can touch to what we can barely see to what we can never reach. We start with the Earth, then the Moon, then the Sun, then nearby stars, then entire galaxies. Each step depends on the one below it. If the first rung is wrong, everything collapses. But it doesn't. It holds. That tells us something profound about the universe. The universe is not designed for intuition. It is not small. It is not gentle. It does not care what feels reasonable. And yet it is understandable. Light travels at a fixed speed. Brightness obeys precise laws. Geometry works the same everywhere. The same physics that bends light near your phone screen also measures galaxies billions of light years away. And here is the part that should stop you for a moment. All of this knowledge, every distance, every explosion, every ancient photon is measured by a fragile species standing on a spinning rock inside a thin layer of air, orbiting an ordinary star. We never left our planet. We never crossed the void. We used thought. We used patience. We used curiosity. The universe did not hand us its secrets. We earned them. And that changes how you should look at the night sky. It is not empty. It is not distant. It is a record of time itself. And you are one of the few things in the universe capable of reading it. That is what this really means. So the next time you look up at the night sky, remember, you are not just seeing stars. You are seeing history, written in light, measured by thought.